Binary star systems are remarkably common in our galaxy, with more than half of all stars estimated to exist in binary or multiple star systems. Among the several mechanisms through which these systems form, disk fragmentation stands as a critical process responsible for creating binary stars with distinctive characteristics. This comprehensive analysis explores the formation of binary star systems through disk fragmentation, examining the physical processes, observational evidence, and properties of resulting systems. Disk fragmentation occurs when gravitational instabilities within a massive accretion disk surrounding a protostar lead to the formation of a secondary star, resulting in a binary system with unique dynamical properties and evolutionary pathways. Binary star systems dominate the stellar population of our galaxy, representing a fundamental outcome of star formation processes. Observational evidence suggests that the tendency of stars to form in pairs or multiples is not merely coincidental, but rather a natural consequence of the physical conditions present during star formation. The prevalence of binary systems necessitates a thorough understanding of how these systems come into existence, with disk fragmentation emerging as one of the primary formation mechanisms. Binary star formation occurs through several distinct mechanisms, with disk fragmentation and turbulent fragmentation standing as the two predominant processes. In turbulent fragmentation, turbulence within a single molecular cloud core leads to multiple dense clumps that independently collapse to form stars that orbit each other. This process typically results in binaries with wider separations and randomly aligned rotation axes. In contrast, disk fragmentation involves gravitational instabilities within an accretion disk surrounding a forming star, causing portions of the disk to fragment into a second protostellar object. This mechanism typically produces more closely orbiting binary systems with potentially aligned angular momentum vectors. The timing of binary star formation proves critical in determining the properties of the resulting system. Observational trends showing a decreasing fraction of binary and multiple systems with age strongly suggest that these systems must form during the earliest stages of cloud collapse, rather than through capture of independently formed stars. This timing indicates that disk fragmentation must occur relatively early in the star formation process, when massive disks are still present around young protostars. Disk fragmentation occurs when a massive accretion disk surrounding a young protostar becomes gravitationally unstable, leading to the formation of a secondary star within the disk material. This process begins with the collapse of a molecular cloud core, which forms a central protostar surrounded by a rotating disk of gas and dust. As the disk accumulates mass from the surrounding envelope, it may become gravitationally unstable if the stabilizing effects of thermal pressure and rotation cannot counterbalance the gravitational forces pulling the material together. The gravitational stability of a protostellar disk is governed by the balance between self-gravity, thermal pressure, and rotational support. When the disk becomes sufficiently massive relative to its central star, gravitational instabilities can develop, forming spiral density waves within the disk structure. These spiral waves can further concentrate material, and if the local density becomes high enough, a self-gravitating clump may form within the disk. This clump can then collapse to form a second protostar, creating a binary system where the secondary star orbits the primary. For disk fragmentation to occur, several physical conditions must be satisfied. The disk must be sufficiently massive compared to its central star, typically with a disk-to-star mass ratio exceeding 10%. Additionally, the disk must be relatively cool, as higher temperatures increase thermal pressure that stabilizes against gravitational collapse. Finally, the disk must be able to cool efficiently, allowing gravitational energy to be radiated away during the collapse process. These conditions are most commonly met in the outer regions of protostellar disks, where cooling is more efficient and orbital timescales are longer. The fragmentation process dramatically alters the structure of the original disk. When a fragment forms, it creates a gap in the disk and begins to accrete its own circumstellar disk from the surrounding material. This leads to a system with a circumstellar disk around each star and potentially a larger circumbinary disk surrounding the entire binary system. The interaction between these disks significantly influences the subsequent evolution of the binary system, affecting orbital parameters and the potential for planet formation. Gravitational instabilities in protostellar disks develop when the self-gravity of the disk becomes significant compared to the stabilizing forces of thermal pressure and differential rotation. These instabilities typically manifest as spiral density waves, which can concentrate material and eventually lead to fragmentation if conditions are suitable. The onset of gravitational instabilities is often described using the Numerical parameter, which balances gravitational forces against pressure and rotational support. When this parameter falls below a critical value, typically around 1, the disk becomes unstable to axisymmetric perturbations. In sufficiently unstable disks, these spiral density waves can grow in amplitude and eventually form self-gravitating clumps. These clumps initially contain only a small fraction of the disk mass, but can rapidly accrete additional material from the surrounding disk. As a clump grows, it forms a local pressure maximum that can trap dust particles, potentially accelerating its growth through both gas and dust accretion. If the clump can continue to collapse and cool efficiently, it will eventually form a protostellar core, the embryo of what will become the secondary star in the binary system. The cooling efficiency of the disk plays a crucial role in determining whether fragmentation will occur. In regions where cooling times are shorter than the local orbital period, fragments can collapse before being sheared apart by differential rotation. Conversely, in regions where cooling is inefficient, the gravitational energy released during collapse heats the gas, increasing pressure support and potentially preventing fragmentation. This delicate balance explains why disk fragmentation typically occurs in the outer regions of protostellar disks, where cooling times are shorter due to lower densities and optical depths. Several processes can trigger or enhance disk fragmentation. External perturbations, such as nearby stellar encounters or infall of material from the surrounding cloud, can induce density fluctuations that seed gravitational instabilities. Rapid infall of material onto the disk can also increase its mass and drive it toward instability. Additionally, the presence of dust can enhance cooling rates through thermal emission, potentially promoting fragmentation in regions that would otherwise remain stable. These various triggering mechanisms help explain the diversity observed in binary systems formed through disk fragmentation. Observational evidence supporting disk fragmentation as a binary formation mechanism comes from various sources, with recent high-resolution observations from facilities like ALMA providing compelling examples. One notable case involves a binary system located approximately 11,000 light-years from Earth, featuring a massive primary star paired with a much smaller companion. This dramatic mass difference strongly suggests different formation mechanisms for the two stars, with the smaller companion likely forming through fragmentation of the disk surrounding the larger star. The physical characteristics of observed binary systems provide clues about their formation mechanisms. Systems formed through disk fragmentation typically exhibit smaller separations and more circular orbits compared to those formed through turbulent fragmentation. Additionally, disk-fragmented binaries often show alignment between the orbital plane of the binary and the rotation axes of the individual stars. However, perfect alignment is not always observed, as subsequent dynamical interactions can alter the orientations of both stellar spins and orbital planes over time. Protostellar disks with substructures such as rings, gaps, and spiral arms have been observed around young stellar objects, providing potential snapshots of the disk fragmentation process. These structures can indicate the presence of gravitational instabilities that may eventually lead to fragmentation. Particularly telling are observations of young protostellar systems with massive extended disks, showing spiral structures and clumpy regions. These features represent the early stages of gravitational instabilities that could potentially develop into stellar companions. Direct observation of the fragmentation process remains challenging due to the embedded nature of young protostars and the relatively short timescales involved. However, indirect evidence comes from statistical studies of binary properties, which show distributions consistent with disk fragmentation models. For example, the correlation between primary star mass and binary frequency, with more massive stars having higher binary fractions, aligns with theoretical predictions that more massive stars tend to form larger disks that are more prone to fragmentation. Binary systems formed through disk fragmentation exhibit distinctive properties that differentiate them from systems formed through other mechanisms. One key characteristic is the mass ratio between the primary and secondary stars. Disk fragmentation typically produces binary systems with unequal masses, often with the secondary star having significantly less mass than the primary. This aligns with observations such as the odd couple system detected by ALMA, where the secondary star has only 1/80 the mass of the primary star. The orbital parameters of binaries formed through disk fragmentation reflect their origin within a protostellar disk. These systems typically have more circular orbits compared to those formed through turbulent fragmentation or capture. The orbital planes of disk-fragmented binaries usually align closely with the original disk plane, although subsequent dynamical interactions can introduce some misalignment. Additionally, the orbital separations tend to be smaller than in binaries formed through other mechanisms, with typical separations ranging from tens to hundreds of astronomical units. Angular momentum alignment represents another characteristic property of disk-fragmented binaries. In principle, stars forming from the same disk should inherit angular momentum from that disk, resulting in alignment between the rotation axes of both stars and their orbital plane. This would produce aligned protostellar outflows, jets emitted from the poles of young, newly forming stars. However, perfect alignment is not always observed, as secondary perturbations and dynamical interactions during and after formation can alter the spin orientations of the stars. Age differences between components of disk-fragmented binaries tend to be smaller than in binaries formed through other mechanisms. Since both stars form from the same initial disk, their formation times are relatively close, typically separated by no more than a few 100,000 years. This contrasts with turbulent fragmentation, where larger age differences can occur if the different cloud fragments collapse at different rates. This synchronicity in formation times has implications for the subsequent evolution of the binary system, particularly regarding the interaction between the circumstellar disks. After fragmentation occurs, the resulting binary system typically features complex disk structures that play crucial roles in the system's subsequent evolution. These disk structures include circumstellar disks around each individual star and potentially a larger circumbinary disk surrounding the entire binary system. The presence and properties of these disks significantly influence the binary's orbital evolution and the potential for planet formation within the system. Circumstellar disks in binary systems formed through fragmentation differ from disks around single stars in several important ways. They are typically truncated by tidal interactions with the companion star, with the truncation radius depending on the binary mass ratio and separation. This truncation limits the size and mass of the circumstellar disks, potentially affecting their ability to form planets. Additionally, these disks may be misaligned relative to each other and to the binary orbital plane, creating complex three-dimensional geometries that influence material flow within the system. Circumbinary disks represent another important component of fragmented systems. These disks surround the entire binary system and can extend to distances many times the binary separation. The inner edge of a circumbinary disk typically features a gap created by tidal forces from the binary, with the gap size proportional to the binary separation. Material from the circumbinary disk can flow through this gap onto the individual circumstellar disks, creating accretion streams that replenish the circumstellar disk material. This ongoing accretion can significantly influence the mass and structure of the circumstellar disks over time. The dynamics of these disk systems create distinctive flow patterns and structures. Gravitational interactions between the binary components and the disks generate spiral density waves, which can transport angular momentum and facilitate accretion. The misalignment between disks can lead to warping and precession, further complicating the system geometry. These dynamic structures affect both the continued evolution of the binary system and the potential for planet formation, with implications for the architecture of any resulting planetary systems. Magnetic fields significantly influence the disk fragmentation process, potentially either promoting or inhibiting fragmentation depending on their strength and geometry. Strong magnetic fields can remove angular momentum from collapsing cloud cores through magnetic braking, potentially reducing disk sizes and making fragmentation less likely. Conversely, in certain configurations, magnetic fields can induce density perturbations that seed gravitational instabilities, potentially enhancing fragmentation. The complex interplay between magnetic fields, rotation, and gravity creates a diverse range of conditions for disk formation and fragmentation. Turbulence represents another critical factor influencing disk fragmentation. Turbulent motions within molecular clouds introduce density and velocity perturbations that can affect both the formation of protostellar disks and their subsequent evolution. These perturbations can seed gravitational instabilities, potentially triggering fragmentation in otherwise stable disks. The simulations described in the search results demonstrate how turbulent initial conditions can lead to filament formation, which subsequently fragments into binary or multiple star systems. This highlights the connection between larger-scale turbulent cloud structures and the smaller-scale process of disk fragmentation. Numerical simulations have been instrumental in understanding the complex interplay of forces involved in disk fragmentation. Adaptive mesh refinement hydrodynamic simulations can model the evolution of marginally stable, turbulent cores with realistic properties matching observations of low-mass molecular cloud cores. These simulations follow the formation of seeds within molecular cloud cores, which accrete mass and eventually launch protostellar outflows. The results reveal how binary and multiple star systems can emerge from filamentary structures in turbulent flows, with virtually all mass flux occurring along these filaments. The transition from isothermal to adiabatic conditions plays a crucial role in determining whether fragmentation occurs. During the early stages of collapse, the gas remains approximately isothermal, as radiation can escape efficiently. As densities increase, the gas becomes optically thick, transitioning to adiabatic behavior, where compressional heating increases the temperature. This transition affects the gene's mass and length, which determine the minimum mass and size of fragments. Numerical simulations using a barotropic equation of state can model this transition and predict its effects on the fragmentation process. Two primary mechanisms dominate binary star formation: disk fragmentation and turbulent fragmentation. These processes produce binary systems with distinctly different properties, providing a way to identify the formation mechanism through observations. Understanding these differences helps astronomers interpret observational data and reconstruct the formation history of observed binary systems. Turbulent fragmentation occurs when turbulence within a molecular cloud core creates multiple dense regions that independently collapse to form separate stars. These stars remain gravitationally bound to each other, forming a binary or multiple system. This process typically results in wider separations between components compared to disk fragmentation. Additionally, since the stars form from different fragments of the cloud, they often have independent angular momentum vectors, resulting in random alignment of their rotation axes and any associated disks or outflows. A key observational signature distinguishing these mechanisms involves protostellar outflows. In disk fragmentation, both stars form from the same disk with shared angular momentum, theoretically producing aligned protostellar jets. In contrast, turbulent fragmentation produces stars with independent angular momentum, resulting in randomly oriented outflows. A study led by Stella Offner using radiation magnetohydrodynamic simulations found that protostellar jets in simulated turbulent fragmentation scenarios were randomly aligned or misaligned, consistent with observations from the masses survey. This supports turbulent fragmentation as a significant mechanism for binary formation, particularly for wider binary systems. The mass ratios between binary components also differ between these mechanisms. Disk fragmentation typically produces more extreme mass ratios, with the secondary star often having significantly less mass than the primary. This occurs because the secondary forms from a fragment of the primary's disk, which contains only a fraction of the total system mass. In contrast, turbulent fragmentation can produce components with more similar masses, as each star forms from a separate gravitational collapse event in the cloud core. The formation of binary stars through disk fragmentation significantly impacts the potential for planet formation within these systems. The presence of a stellar companion alters disk properties through tidal truncation, dynamical heating, and changes in the radiation environment. These modifications affect the conditions for planet formation, potentially either inhibiting or enhancing it in different regions of the system. In circumstellar disks within binary systems, tidal interactions with the companion star truncate the outer disk regions, reducing the total mass and size of the disk. This truncation can limit the reservoir of material available for planet formation, potentially making it more difficult to form giant planets that require substantial solid material. However, the tidal forces can also concentrate material at certain locations within the disk, potentially accelerating planet formation in these regions. The effectiveness of planet formation thus depends on the specific binary parameters, particularly the separation and mass ratio. Circumbinary disks present unique environments for planet formation. The inner regions of these disks contain a gap opened by the gravitational influence of the binary, creating a hostile environment for planet formation. Beyond this gap, however, the disk can be quite massive and stable, potentially providing favorable conditions for planet formation. Planets forming in these regions would orbit around both stars, creating distinctive planetary architectures. Observations have indeed confirmed the existence of circumbinary planets, demonstrating that planet formation can succeed in these environments despite the complications introduced by the binary dynamics. The misalignment of disks in binary systems formed through fragmentation introduces additional complexity to the planet formation process. When circumstellar disks are misaligned relative to each other or to the binary orbital plane, the resulting gravitational torques can induce warping, precession, and potentially disruptive tidal effects. These dynamic influences can alter the collision velocities of planetesimals, affecting their ability to grow into larger bodies. Consequently, planet formation in misaligned disk systems may follow different pathways compared to aligned systems or disks around single stars. Numerical simulations have been instrumental in advancing our understanding of disk fragmentation processes. These computational tools allow researchers to model the complex interplay of gravity, hydrodynamics, magnetic fields, and radiative transfer that govern disk evolution and fragmentation. Modern simulations employ sophisticated techniques such as adaptive mesh refinement to resolve the wide range of spatial scales involved in the fragmentation process, from the large-scale disk to the small-scale fragments. High-resolution three-dimensional simulations have revealed the critical importance of properly resolving the gene's length to accurately model fragmentation. These simulations start with realistic initial conditions, incorporating observed properties of molecular cloud cores such as density profiles, rotation rates, and turbulent velocity fields. By following the collapse and fragmentation of these cores, researchers can identify the conditions that lead to binary formation and determine the properties of the resulting systems. Simulations have demonstrated the formation of binary stars along filamentary structures in turbulent flows. These filaments serve as conduits for mass flux, with densities typically 1 to several orders of magnitude greater than the ambient medium. Virtually all mass accretion occurs along these filaments, highlighting their importance in the star formation process. As protostars form at the ends of these filaments, they develop their own circumstellar disks, which may be misaligned relative to each other due to the turbulent nature of the formation process. Theoretical models complement numerical simulations by providing analytical frameworks to understand disk fragmentation. These models often focus on the criteria for gravitational instability, using parameters such as the Tumri Q value to predict when disks become unstable. They also address the cooling requirements for fragmentation, as fragments can only survive if they can cool efficiently. These theoretical frameworks help interpret simulation results and connect them to observable properties of binary systems. Current research on disk fragmentation focuses on integrating increasingly sophisticated physics into numerical models. This includes improved treatments of magnetic fields, radiative transfer, and non-ideal magnetohydrodynamic effects. These advancements allow for more realistic simulations of disk formation and evolution, providing better predictions of when and how fragmentation occurs. Additionally, researchers are investigating the role of chemistry and dust physics in the fragmentation process, as these factors affect the cooling properties of disks and thus their stability against fragmentation. Observational facilities like ALMA continue to provide unprecedented views of protostellar disks, revealing complex structures that may be precursors to fragmentation. These observations allow direct comparison with theoretical predictions and help constrain the models. Future facilities such as the next-generation Very Large Array and space-based infrared observatories will provide even more detailed views of disk structures and potentially capture fragmentation events in action. The connection between disk fragmentation and planet formation represents an active area of research, as both processes involve the concentration of material within disks. Understanding their relationship is crucial for developing a comprehensive theory of star and planet formation. Researchers are investigating how the competition between these processes affects the resulting architecture of planetary systems in binary stars, and how observations of both binaries and exoplanets can constrain these theories. Statistical studies of binary star properties provide another avenue for testing fragmentation theories. By comparing the distributions of properties like mass ratios, separations, and alignments with the predictions of different formation models, researchers can determine the relative importance of different formation mechanisms. Expanding these statistical samples, particularly for very young systems where the formation signatures remain clear, represents an important goal for future observational campaigns. Disk fragmentation represents a fundamental process in the formation of binary star systems, producing binaries with distinctive properties that reflect their origin within protostellar disks. Through this mechanism, gravitational instabilities within massive accretion disks lead to the formation of secondary stars, creating systems that often feature unequal mass components, relatively close separations, and complex disk structures. The process involves a delicate balance of gravitational, thermal, and rotational forces, influenced by factors such as turbulence, magnetic fields, and cooling efficiency. Observational evidence supporting disk fragmentation comes from facilities like ALMA, which have revealed binary systems with properties consistent with this formation mechanism. These observations, combined with numerical simulations and theoretical models, have significantly advanced our understanding of how binary stars form and evolve. The ongoing research in this field continues to refine our knowledge of the conditions necessary for fragmentation and the resulting properties of the binary systems produced through this process. The formation of binary stars through disk fragmentation has profound implications for planet formation, creating unique environments that differ significantly from those around single stars. Understanding these environments and their influence on planet formation processes remains an active area of research, with implications for our broader understanding of planetary system architectures and the potential for habitable worlds in binary systems. As observational capabilities and computational resources continue to improve, our understanding of disk fragmentation and its role in shaping stellar and planetary systems will undoubtedly advance further.